Introduction. A medical shop contains a vast number of medicines. The shopkeeper finds difficult or impossible to remember all the names of medicines that he has. When you go to a medical shop and ask the shopkeeper for a particular medicine, he hands over it to you without any difficulty. How is it possible? For any system involving several things, a particular order of arrangement of those things is essential. Even in chemistry, from the earliest times, scientists have been trying to classify the available elements on the basis of their properties. Robert Boyle, 1661, defined an element as any substance that cannot be decomposed into a further simple substance by a physical or chemical change. At his time, about 13 elements were known. Towards the end of the 18th century, by the time of Lavoisier, another 11 elements were discovered. By 1940, a total of 91 elements from natural sources and another 17 elements synthetically were obtained. Now, including synthetic elements, there are more than 115 elements. As the number of elements increased, it became difficult to keep in memory and chemistries of individual elements and their compounds. So, there was a need to classify them in other ways. Hence, chemists started to frame ways to group these elements and compounds on the basis of their physical and chemical properties. In the beginning of the 18th century, Joseph Louis Ross stated that hydrogen atom is the building material and atoms of all other elements are simply due to the combination of number of hydrogen atoms. Note: at Louis Ross' time, the atomic weights of all elements were given as whole number and atomic weight of hydrogen was taken as 1. Doberener's law of triads. A German chemist, John Wolfgang Doberener, in 1829 noted that there were groups of elements with 3 elements known as triads in each group with similar chemical properties. He tried to give a relationship between the properties of elements and their atomic weights. Doberener stated that when elements with similar properties are taken 3 at a time and arranged in the ascending order of their atomic weights, the atomic weight of the middle element is the average of the atomic weights of the first and third elements. This statement is called the Doberener's law of triads. Activity. Observe the following table. In the first row, we will find that atomic weight of sodium Na is equal to the average relative atomic weight of Li and K. Can we establish the same relationship with the set of elements given in the remaining rows? Except in the first row, we cannot establish the relationship as set by law of triads. Find average atomic weights of first and third elements in each row and compare it with the atomic weights of the middle elements. From table, we observe that except group A, in the remaining groups, the average of atomic weights of first and third elements is roughly equal to the middle elements. Taberner's attempt gave a clue that atomic mass could be correlated with properties of elements. Limitations. All the known elements at that time could not be arranged in the form of triads. The law failed for very low mass or for very high mass elements. In case of F, Cl, Br, the atomic weight of Cl is not an arithmetic mean of atomic weights of F and Br. As the techniques improved for measuring atomic masses accurately, the law was unable to remain strictly valid. Newland's law of octaves. John Newlands was a British chemist. Newlands, in 1865, found that when elements were arranged in the ascending order of their atomic weights, they appeared to fall into 7 groups. Each group contained elements with similar chemical properties based on their observations. Newlands proposed the law of octaves. Law of octaves. The law of octaves states that when elements are arranged in ascending order of their atomic weights, they fall into a pattern in which their properties repeat at regular intervals. Every eighth element starting from a given element resembles in its properties to that of the starting element. Elements with similar chemical properties are presented along the horizontal row. According to Newland's table, if we start with hydrogen and move down and then start at the top to 8th element is fluorine and next 8th element is chlorine and so on. The properties hydrogen, fluorine and chlorine are similar. Similarly, if you start at lithium, then 8th element is sodium and next coming 8th is potassium and so on. These elements shown similar physical and chemical properties. Unfortunately, his work was either accepted by his seniors nor by the Journal of the Chemical Society, which rejected its publication. Because of Newland's law of octaves has some limitations, there are instances of 2 elements fitted into the same slot. Example, CO and Ni. Certain elements totally dissimilar in their properties were fitted into the same group. The law was not valid for elements that had atomic masses higher than calcium. Example, Newlands arranged CO, Ni, Pd, Pt and Ir, which have different properties, compared with halogens in the same row. Therefore, the law of octobase holds good only for the elements up to calcium. The law was not valid for elements that had atomic masses higher than calcium. This table was restricted to only 56 elements and did not leave any room for new elements. He tried to link periodicity of the chemical properties of elements with the periodicity found in the music. Do you know? Are you familiar with musical notes? In the Indian system of music, there are 7 musical notes in a scale: Sa, Re, Ga, Ma, Pa, Da, Ne. In the West, they use the notations do, re, mi, fa, sa, la, ti. Naturally, there must be some repetition of notes. Every eighth note is similar to the first one, and it is the first note of the next scale. Mendeleev's periodic table. Mendeleev arranged the elements known at that time in a chart in a systematic order in the increasing order of their atomic weights. He divided the chart into 8 vertical columns known as groups. Each group is divided into A, B subgroups. Each column contained elements of similar chemical properties. The elements in the first column, for example, react with oxygen to form compounds with the general formula R2O. For example, Li, Na, and K, when react with oxygen and form compounds Li2O, Na2O, and K2O respectively. Elements of the second column react with oxygen to form compounds with the general formula RO. For example, Pe, Mg, and Ca, when react with oxygen, form PeO, MgO, and CaO. Mendeleev tried to explain the similarities of elements in the same group in terms of their common valency. The periodic law. Based on Mendeleev's observations regarding to properties of elements in the periodic table, a law known as the periodic law of the properties of elements was proposed as follows. The law states that the physical and chemical properties of the elements are a periodic function of their atomic weights. Mendeleev's periodic table of 1871 version. Silent features. Groups and subgroups. There are 8 vertical columns called groups, represented by Roman numerals 1 to 8. Each group is divided into 2 subgroups A and B. The elements represent in a group and its subgroups have similar properties. For example, subgroup Ia elements called alkali metals, that is Li, Na, K, Rb, Cs, and Fr. Periods. The horizontal row in Mendeleev's table are called periods. There are 7 periods denoted by Arab numerals 1 to 7. A period comprises the entire range of elements after which properties repeat themselves, predicting the properties of missing elements. Based on the arrangement of the elements in the table, he predicted that some elements were missing and left backspace at the appropriate places in the table. He named those elements tentatively by adding the prefix eka, that means 1, to the name of the element immediately above the each empty space. Example, eka boron, eka aluminium, and eka silicon were close to the observed properties of scandium, gallium, and germanium respectively, which were discovered later. Correction of atomic mass. The correct placement of elements in Mendeleev's periodic table helped in correcting the atom masses of some elements like beryllium, indium, gold. Anomalous series. Some anomalous, that is, irregular series of elements like Te and I were observed in the table. The anomalous series contained elements with more atomic weight like Te placed before the element with less atomic weight like I. Do you know? Mendeleev said about the melting point of a car, Ai, as if I hold it in my hand. It will melt. The melting point of Ga is 30.2 degrees Celsius and our body temperature is 37 degrees Celsius. Limitations of Mendeleev's periodic table. Anomalous pair of elements. Certain elements of highest atomic weights predict those with lower atomic weights. Example: tellurium, atomic weight 127.6, Praseodymium iodine, atomic weight 126.0. Dissimilar elements placed together. Elements with dissimilar properties were placed in same groups as subgroup B. Example: alkali metals like Li, Na, K, etc. of Ia group have little resemblance with image metal like Cu, Ag and Au of Ib group. Cl is of 7A group and Mn is of 7B, but chlorine is a non-metal where Mn is a metal. Do you know? At the time when Mendeleev introduced his periodic table, even electrons were not discovered. Even then, the periodic table was able to provide a scientific base for the study of chemistry of elements. In his honor, the 101th element was named Mendeleevium. H.J. Moseley in 1913 found that each element emits a characteristic pattern of X-rays when subjected to bombardment of high-energy electrons. By analyzing the X-ray patterns, Moseley was able to calculate the number of positive changes in the atoms of respective elements. The number of positive charges, that is protons, in the atom of an element is called the atomic number of the element. The atomic number is more fundamental characteristic of an element than its atomic weight. It was recognized that a better way of arranging the elements in the periodic table is according to the increasing atomic number. This atomic number concept forced the periodic law to be changed. Example: tellurium, Te, has more atomic weight than iodine, I. It has atomic number less by 1 unit compared to iodine. The periodic law is changed from atomic weight concept to atomic number concept, and now it is called the modern periodic law. Mendeleev's periodic table depends on the atomic weight. The modern periodic law may state as the physical and chemical properties of elements are the periodic function of the electronic configurations of their atoms. The physical and chemical properties of elements depend on the number of electrons and their arrangements in atoms. Atomic number of an element Z indicates not only the positive charges, that is, the protons in the nucleus of the atom or the element, but also the number of electrons in the neutral atom of that element. This modern table is called the long form of the periodic table. Positions of elements in the modern periodic table. The horizontal rows in the long form periodic table is called periods. They are 7 periods. The number of main shells present in the atom of particular element decides to which period belongs to. Example: hydrogen H and helium He atoms contain only one main shell K. Therefore, they belongs to period 1. The elements Li, Be, P, C, N, O, F and Ne contain 2 main shells, that is K and L, in their atoms. Therefore, they belong to period 2. The number of elements in a period depends on how electrons are filled into various shells. Each period starts with a new shell and ends when shell is filled with respect to the S and P levels of its main shell. The first contains 2 elements because the K shell contains only one subshell, that is 1s, which can accommodate 2 electrons only. The second period starts with the second main shell, L, which has 2 subshells, 2s and 2p, which can accommodate 8, that is 2 plus 6 electrons. Thus, the second period consists 2 s block elements, that is Li, Pe, and 6 p block elements, P to Ne. Hence, second period contains 8 elements. Third period starts with third main shell, N, which has 3 subshells, 3s, 3p and 3d, but while electrons are being filled into the shell, 3d gets electrons only after 4s is filled. Therefore, the third period contains again 8 elements by filling 3s and 3p. Fourth main shell, N, has 4 subshells, 4s, 4p, 4d and 4f, but while filling electrons, they are filled in the order 4s, 3d and 4p. Due to this, fourth period contains 18 elements, that is 2 plus 10 plus 6, which includes 2 s block, that is K, Ca, 10 elements from D block, that is Sc to Zn, and 6 elements from P block, that is 31Ga to 36Kr. Similarly, fifth period contains 18 elements, that is from 37Rb to 54Xe. Sixth period contains 32 elements, that is from 55Cs to 86Rn. Seventh period is incomplete and contains 3 elements from S block, 14 elements from F block, 10 elements from D block, some elements from P block. The 4F elements, that is lanthanoids, and 5F elements, acetinoids, are shown separately at the bottom of the periodic table. Periodic properties of the elements in the modern table. The modern periodic table is organized in the basis of the electronic configuration of the atoms of elements. Physical and chemical properties of elements are related to their electronic configurations, particularly the outer shell configurations. The atoms of the elements in a group possess similar electronic configurations. We expect all the elements in a group should have similar chemical properties, and there should be a regular gradation in their physical properties from top to bottom. Similarly, across the table, that is, from left to right, in any periodic elements get an increase in the atomic number by 1 unit between any two successive elements. Therefore, the electronic configuration of valency shell of any two elements in a given period is not same. Due to this reason, elements along a period possesses different chemical properties with regular gradation in their physical properties from left to right. To understand this, we will take some properties of elements and discuss how they vary in groups and in periods. Properties of elements and their trends in groups and in periods. Valence or valency of an element was defined as the combining power of an element with respect to hydrogen, oxygen, or indirectly any other element through hydrogen and oxygen. Valency of an element with respect to hydrogen is the number of hydrogen atoms with which one atom of that element chemically combines. Valency of an element with respect to oxygen is twice the number of oxygen atoms with which one atom of that element combines. Example: one atom of Na chemically combines with one atom of H to give NaH. Therefore, the valency of Na is 1. One atom of Ca combines with one atom of O to give CaO. So, the valency of Ca is 2. In general, the valence of an element with respect to hydrogen is its traditional group number. If the element is in the group V or above, its valency is 8 group number. For example, chlorine valency is 8 minus 1 equals to 1. In general, each period starts with valency 1 for first group elements, increases up to 4 with respect to the group number, and then decreases from 4 to 3 to 2 to 1 to 0 in the following groups. That is, this is applicable only for main group elements, that is, S and P block elements. Nowadays, the valence of an element is generally taken as the number of valence shell, that is, outermost shell, electrons in its atom. Oxidation number concept almost is the latest substitute to the valence concept in the modern literature. Properties of elements and their trends in groups and in periods. Valence or valency of an element was defined as the combining power of an element with respect to hydrogen, oxygen, or indirectly any other element through hydrogen and oxygen. Valency of an element with respect to hydrogen is the number of hydrogen atoms with which one atom of that element chemically combines. Valency of an element with respect to oxygen is twice the number of oxygen atoms with which one atom of that element combines. Example: one atom of Na chemically combines with one atom of H to give NaH. Therefore, the valency of Na is 1. One atom of Ca combines with one atom of O to give CaO. So, the valency of Ca is 2. In general, the valence of an element with respect to hydrogen is its traditional group number. If the element is in the group V or above, its valency is 8 group number. For example, chlorine valency is 8 minus 1 equals to 1. In general, each period starts with valency 1 for first group elements, increases up to 4 with respect to the group number, and then decreases from 4 to 3 to 2 to 1 to 0 in the following groups. That is, this is applicable only for main group elements, that is, S and P block elements. Nowadays, the valence of an element is generally taken as the number of valence shell, that is, outermost shell, electrons in its atom. Oxidation number concept almost is the latest substitute to the valence concept in the modern literature. Metals and non-metals. We have learned about the properties of metals in the chapter Metals and Non-metals in class 8. The elements with 3 or less electrons in the outer shell are considered to be metals, and we may find some exceptions to this. D block elements, that is, 3rd group to 12th group, are metals decreases gradually from left to right in periodic table. Lanthanoids and actinoids actually belong to 3rd group, which is within the transition elements. Hence, they are called the inner transition elements. Metalloids or semi-metals are elements which have properties that are intermediate between the properties of metals and non-metals. They possess properties like metals but brittle like non-metals. They are generally semiconductors. Example: P, Si and Ge. All elements in S block are metals, whereas in P block, that is, except 18th group, there are metals, non-metals and metalloids. In periodic table, you will notice a staircase like demarcation. The elements to the left of this demarcation are metals and to the right are non-metals. The elements on staircase or very near to it like P, Si, As and Ge, etc. are metalloids. Metallic and non-metallic properties. Metals generally show less electronegative character. In compounds, they generally show a tendency to remain as positive ions. This property is often termed as electropositive character. Metals are electropositive elements. Non-metals are generally more electronegative due to their smaller atomic radii. Example: third period, Na, Mg, Al, Si, P, S, Cl. We know that Na and Mg are metals. Ai and Si are semi-metals, that is, metalloids. P, S and Cl are non-metals. So, we find metals on left side and non-metals on right side of the periodic table. This means metallic character decreases while non-metallic character increases as we move along a period. Let us take group 14 elements. For a group is to C, Si, Ge, Sn and Pb. Here also we know that carbon is non-metal. Si and Ge are metalloids. Sn and Pb are metals. So, we find non-metals particularly at the right-hand side top and metals at the left and right-hand side bottom of the periodic table. This means metallic character increases while non-metallic character decreases in a group as we move from top to bottom. Activity: find out the valencies of first 20 elements. How does the valency vary in a period on going from left to right? How does the valency vary on going down a group? Atomic radius. Atomic radius of an element may be defined as the distance from the center of the nucleus of the atom to its outermost shell. Atomic radius of an element is not possible to measure in its isolated state because it is not possible to determine the location of the electron that surrounds the nucleus. However, we can measure the distance between the nuclei of adjacent atoms in a solid. From this, we can estimate the size of the atom by assigning half of this distance to the radius of each atom. This method is best suited to elements such as the metals that exist in the solid state. More than 75% of the elements are metals, and atomic radii of metals are called metallic radii. Atomic radius is measured in pm, that is, picometer units. Variation of atomic radii in group. In a group, as we go down, the atomic nucleus of the element increases. Hence, a new shell is added. As a result, the distance between nucleus and the outer shell increases. This is the reason why the atomic radius increases as we go down in a group. Variation of atomic radii in period. Atomic radii of element decreases across a period from left to right. As we go from left to right, electrons enter into the same main shell or even inner shell, but nuclear charge increases. Hence, the nuclear attraction on the outer shell increases. As a result, the size of the atom decreases. Do you know? How are the names of certain families of periodic table derived? Alkali metal family. Alkali equals to plant ashes. Na, K, etc. were obtained from plant ash, group La elements are called alkali metal family. Chalcogen family. Chalcogenous equals to ore product as the element in group 16 from ores with metals. They are called as chalcogenous family. Halogen family. Halos equals to sea salt. Genus equals to produced. As most of the elements in group 17 are obtained from nature as sea salt, they are called as halogen family. Noble gases. As the element of group 18 are chemically least active, they are called as noble gases. Their outer shell electronic configurations are basis for octet rule. Activity. Some main group elements of S block and P block have family names as given in the following table. Observe the long form of the periodic table and complete the table with proper information. Do you know? IDE means hair, and it is used generally for a change like Cl plus to Cl minus. Cl is chlorine atom and Cl minus is chloride ion. OID means the same. Some scientists suggest lanthanoids as 57 La to 70 Yb. Some suggest them as 58 Ce to 71 Lu, and some take 57 La to 71 Lu. There is another arrangement that even 21 Sc and 39 Y should be included in lanthanoids. All these suggestions have instance because 21 Sc, 39 Y and 57 La to 71 Lu all have the similar outer shell configuration. Also, in the case of actinoids, these are different arguments like are from 90th to 103 Lr or 89 Ac to 102 NO or 89 Ac to 103 Lr. Do the atom of an element and its ion have same size? Let us assume that sodium Na atom has lost an electron and formed a quotient of sodium. Which one between Na and Na plus would have more size? Why? Atomic number of sodium, that is Na, is 11 and it contains 11 protons and 11 electrons with outer electron as 3s1. On the other hand, Na plus ion has 11 protons but only 10 electrons. The 3s shell of Na plus level has no electron in it. Hence, its outer shell configuration is 2s2, 2p6. As proton number is more than electron in it, the nucleus of Na plus ion attracts outer shell electrons with strong nuclear force. As a result, the Na plus ion shrinks in size. Therefore, the size of Na plus ion is less than Na atom. In general, the positive ion of an element has less size than its neutral atom. Consider another example. Assume that chlorine atom has gained an electron to form an ion of chlorine Cl minus, that is, chloride ion. Which one between Cl and Cl minus would have more psi? Why? Electronic configuration of chlorine, that is Cl atom, is 1s2, 2s2, 2p6, 3s2, 3p5, and the electronic both chlorine and chloride ion have 17 protons each, but there are 17 electrons in chlorine atom, whereas 18 electrons in chloride ion. Therefore, the nuclear attraction is less in Cl- ion when compared with chlorine ion. Therefore, the size of the chlorine Cl atom is less size than Cl- ion. In general, negative ion of an element has bigger size than its neutral atom. Ionization energy. The energy required removing an electron from the outermost orbit or shell of a nuclear gaseous atom is called ionization energy. The energy required to remove the first electron from the outermost orbit or shell of a neutral gaseous atom of the element is called its first ionization energy. The energy required to remove the electron from unipositive ion of the element is called second ionization energy of that element, and so on. M gas plus IE1 gives M plus gas plus E minus, that is IE1 equals to first ionization energy. M plus gas plus IE2 gives M plus 2 gas plus E minus, that is IE2 equals to second ionization energy. Ionization energy of an element depends on its nuclear charge. More the nuclear charge, more is the ionization energy. Example, between 11 Na and 17 Cl, chlorine atom has more ionization energy. Screening effect or shielding effect. The shells with electrons between nucleus and the valence shell act as the screens and decrease nuclear attraction over valence electron. This is called the screening effect. More the screening effect, less is the ionization energy. Example, between 3 Li and 55 Cs, with more inner shells has less ionization energy. Penetration power of the orbitals. Orbitals belonging to the same main shell have different piercing power towards the nucleus. Example, 4s is greater than 4p, is greater than 4d, is greater than 4f in the penetration. It is easier to get 4f electron than 4s. Between 4be, that is 1s2, 2s2, and 5b, that is 1s2, 2s2, 2p1, the element 5b has less ionization energy due to less penetration power of 2p compared to 2s. Stable configuration. It is easier to remove one electron from 8O, that is 1s2, 2s2, 2p4 than 7n, that is 1s2, 2s2, 2p3. This is because 7n has stable half-filled configuration. Atomic radius. As atomic radius increases, the ionization energy decreases. Example, IE of F is greater than that of I, because the atomic radius of I is more than air. Electron affinity. The electron affinity of an element is defined as the energy liberated when an electron is added to its neutral gaseous atom. Electron affinity of an atom is also called electron gain enthalpy of that element. M gases plus E minus gives N minus gas plus Ea. Ea equals to electron affinity. The energy liberated when an electron is added to a uni-negative ion of the element is called the second electron affinity of that element. However, practically no element shows liberation of energy when the second electron is added to its uni-negative ion. Variation in group. Electron gain enthalpy values decrease as we go down in a group due to increase in atomic radius. Variation in period. Electron gain enthalpy values increase as we go from left to right in a period due to decrease in atomic radius. Electron affinity values of halogens are, that is, in kg mole 1, F minus 328, Cl minus 349, Br minus 325, I minus 295 kg mole per 1. Similarly, for group 16 elements, the electron gain enthalpies are O minus 141, S minus 200, Ge minus 195 and Te minus 190 kg mole per 1. Electronegativity. The electronegativity of an element is defined as the relative tendency of its atom to attract electrons towards itself when it is bounded to the atom of another element. All the factors that influence the ionization energy and the electron affinity of elements influence the electronegativity values of those elements. Because of this, Millikan proposal that the electronegativity of an element is the average value of its ionization energy and electron affinity. Electronegativity equals to ionization energy plus electron affinity by 2. Variation in groups and periods. Electronegative values of elements decrease as we go down in a group and increase along a period from left to right. Pauling assigned the electronegativity values for elements on the basis of bond energies. He assumed that the electronegativity of hydrogen is 2.20 and calculated the values of other elements with respect to hydrogen. Observe the values in the following example. Fluorine has the highest electronegativity, which is of 4, and CS has lowest electronegativity, which is of 0.79.